I wanted to talk about this phase diagram. It's in the book. So we can change the phase of things. We're sort of familiar with temperature, changing the phase with temperature. But we can also do it with pressure. And so if we're at a certain pressure, we know that we go from a solid. As we heat up a solid, it typically goes through the liquid phase, and then it goes into the gas phase, right? So at a particular pressure, we add heat, the temperature goes up. Eventually it melts and becomes a liquid. Eventually it vaporizes and boils and becomes a gas. But if we change the pressure, we could get to a point where it goes from a solid directly to a gas without passing through a liquid state. Maybe you're familiar with dry ice, solid CO2. At atmospheric pressure, it falls in this region here. It goes directly from a solid to a gas. That's why we call it dry ice. You put a chunk of it in a package with some perishable items and ship them off somewhere to a friend. And as it changes state, it doesn't make the package all wet, and FedEx doesn't get upset with you. That's called sublimation. When something goes from a solid to a gas without passing through a liquid state, we call that sublimation. Increase the pressure, and you go back to sort of what we're familiar with. Or think about it vertically. When you are at a fixed temperature, maybe you have a liquid, and you increase the pressure. What happens when you increase the pressure of a liquid? Well, those molecules get pushed tighter and tighter together. And so this is the curve for most substances. When a liquid gets pushed and compact and the molecules get more and more dense, it becomes a solid. Most substances, a solid is more dense than a liquid. So this is a curve for most substances that we're familiar with. But there's one common substance that does not happen with: water. Water, ice cubes float, right? Ice is less dense than the liquid. It's a very unusual thing. And so this curve actually shifts the other way for water. So if you're in the solid state and you increase the pressure, it goes to a liquid. Let me draw it for you. And so this is why for water, you're in a solid state, you compact it more, you increase the pressure, and it actually becomes more dense. In its liquid state, it becomes a liquid. Very unusual. But that's why ice skates work so efficiently. The small blade on the ice skate, all your weight pressing on that small area is a very high pressure. It hits the ice, it's pressing on the ice with that high pressure, and it actually causes the ice to melt, and that's what makes it so slippery. And you can glide so effortlessly with ice skates because the pressure causes the ice to melt underneath the blade. So it's a little unusual. Most substances have this more like this. So think a little bit about what's happening. You know, when you're at a constant temperature, you can change the pressure to go from a solid to a liquid. When you're at constant pressure, we can change the temperature. And of course, you can have any combination. But we get some interesting effects, especially when you get below the triple point. So the triple point, you can have all three phases present at the same temperature. So for water, that point is very, very low temperature and pressure. It doesn't occur very easily. But for other substances, it might occur at temperatures and pressures that are closer to what we're familiar with. So we've talked about the fact that it takes energy to change the temperature of a substance. And what I want to walk you through is actually including the phase changes as well. So let's start with something we know about, ice at negative 50 degrees. So I've got temperature on my vertical axis, so there will be minus 50 degrees C. And we'll have heat on the horizontal axis. So we're going to add some heat. What happens? The ice warms up until it gets to 0 degrees. And then what happens? We add more heat, but the ice doesn't go above 0 degrees. It starts to melt. And it stays at 0 degrees until all the ice has melted. Now we have liquid water at 0 degrees. We add more heat. We can change the temperature of the water. It's going to increase until it gets to 100. Oops. It's going to increase in temperature until it gets to 100 degrees C. And then we're going to try to add some more heat, and it's going to boil. And it's going to stay at 100 degrees C because as we add more heat, what happens, the molecules that become a gas take that heat away. So it stays at 100 degrees C until all the water is boiled. And then if we continue to add heat, the gas molecules heat up and go hotter and hotter, move faster and faster. So we end up with a plot that looks something like this. So you have to remember that these phase changes take a lot of energy. It takes a lot of energy to get something to melt or evaporate. And so the temperature remains the same as the phase change is occurring, even though we're still putting a lot of energy in, because it takes energy to change the phase. So an interesting calorimetry problem now is one that not only involves the temperatures, finding an equilibrium temperature. Maybe you're mixing a hot metal with cool water, finding the equilibrium temperature. But now maybe we can mix in ice and see what happens, including this, where we include the energy it takes to change the phase of the substance.